Graphical analysis of kinematics in one dimension. An object moves along a straight line and the velocity on the y-axis here as a function of time on the x-axis is shown on the graph. Find the acceleration of the object for the time intervals 0 to 5 seconds, 5 to 10, 10 to 15, 15 to 20, 20 to 25, and finally 25 to 30. Then find the travel distance of the object from t equals 0 to t equals 30 seconds. And finally, find the displacement of the object from t equals 0 to t equals 30 seconds. Find the acceleration of the object for these various time intervals. And the first thing we're going to notice is it will be constant, because if you look at the velocity time graph, all the pieces are straight lines. And the slope of a straight line is always a constant. That means the acceleration will be constant, which means the acceleration at any point is equal to the average acceleration, and that's going to be v final of the interval minus the initial velocity divided by the time. So again, constant acceleration for every one of these pieces, and what we're going to do is, hang on, let's erase that over here, and what we're going to do is pick off the velocities for every time interval. So the first one, at time equals 5, the velocity is 4. Time equals 0, velocity is 0. So let's go to the next slide and start doing that. We'll do the first three intervals, which is 0 to 5, 5 to 10, and then 10 to 15. And here is 0 to 5. You see the velocity at the 5-second point is 4. There's 4. At the 0 second, it's 0. You divide by 5, which is the time interval. It's a 5-second interval. And we get 0.8 meters per second squared. Now, let's go to the next one. This point here, okay, you've got at 10 seconds, it's 4. And also at 5 seconds, it's 4. So you have 4 minus 4 over 5. That's 0 meters per second squared. What do you notice about this acceleration? Well, it's just the slope of the line, right? Because the average acceleration is equal to the acceleration at any point, so we're just taking the slopes of these various lines. So just looking at this guy without even doing a subtraction, clearly it looks just like this, except it's in the opposite direction. It will have a negative slope, so that will be negative 0.8 meters per second squared. We continue. And we can either go ahead and pick off the points like it is done here, or just use a little analysis here. Whatever the slope was here, it's going to be the same here for the 15 to 20 interval. So that'll be negative 0.8 again. Slope here, 0. There you go. And you can see how this line here is parallel here, so it has the same slope, also 0.8 meters per second squared. We want to find the travel distance of the object from 0 seconds to 30 seconds. On a velocity time curve, you can find the distance and the displacement by taking the area under the curve. Because let's see, if we have velocity in the y direction, time in the x direction, what's velocity times time? Well, that's just position. So we're going to have one area here, and then we're going to have another one over here. Now, we can't just, well, we can. We can split these into easily recognizable shapes. Like there's a triangle, here's another triangle, and here's a rectangle. Or we can recall the trapezoid formula. And that's what we're going to use. It's base 1 plus base 2. And that's, here's base 1. You know what, let me erase that again. Here's base 1, here's base 2, divided by 2 times the height. And this will be the height like this. So the area of our first shape over here, the one base is 15, the top is 5, divide by 2, the height is 4, so that area is 40. And 2 is just the mirror image of it, so the area of this is also 40. Now we're talking about the total distance traveled. So that doesn't worry about where we start and when we finish. It's just how many steps did we take? How much distance did we cover? So both of these will be positive, because if you're walking here, in both cases, you're walking, expending the same energy, and your feet are going the same amount of meters. So we're just going to add those two numbers together, and our total distance will be 40 plus 40, 80 meters. That's our distance. Displacement, which is what we're finding now, is different than distance. There, it matters what direction we're going in. So in this first case, since we had a positive velocity, we were going in the positive direction, and we covered 40 meters. 40 meters. Then what happened? At this point here, we turned around and started heading with a negative velocity. So we're heading back to where we started from, and we covered this distance, which is actually a displacement of negative 40 meters. Mathematically, you can see that because what's the height here? Well, the height's negative 4. So if we plug it into the equation, and we care about the signs now because it's displacement, our total displacement will be 0. We're back where we started from. This guy here, we spent moving away from our position in the positive direction, turned around at this point, and started moving back with the same types of velocity for the same amounts of time. So we just wound up back where we started. Displacement is 0 meters.